Everybody got silent as soon as I started recording. Okay, very good.
Shall I start?
So yeah, Iain will deliver his second lecture on Intro to TMDs. And he posted a couple links again on the Slack page where you can see these the content of these slides and follow along on your own computer if you prefer. So take it away, Iain.
Yes. So just a word about that. I posted both the file that I'll be editing as well as a more complete version that should look like what this one looks like after we're done. It's a rough approximation, so you can use either one. All right, so let's start out by reminding us what we did in lecture one. So in lecture one, we were peeling the onion of TMDs, and we'd gotten through layers 1, 2, and 3. One was understanding factorization. 2 was also understanding factorization in more detail, and in particular, the kind of ingredients that come into an actual TMD. 1 was more about the factorization of cross sections. And then 3, we got to the operator definitions. And this was a key formula that we had for the renormalized TMD part-time distribution function as a limit, as the UV cutoff is removed, as some rapidity cutoff that we haven't yet talked about in detail, and we'll talk about in detail today. But as that rapidity cutoff is removed, there's some UV renormalization, and there's what's called an unsubtracted TMD PDF or beam function. Sometimes, usually the beam function is this combination that's the unsubtracted TMD PDF divided by subtractions, and then a soft function. And we had matrix element definitions of these objects. So here, this numerator, which should have a tilde on it, is given by this matrix element of quark fields with it connected by a staple Wilson line. So you think about this picture, and there's a staple, it goes off to infinity and backwards in time here to minus infinity. And it connects the two quarks at different space-time points, separated by a transverse distance bt and also a distance along the light cone b minus. And then there was this square root of this function is a matrix element of a closed loop here. Again, it extends back to minus infinity here. Along the line, the TMD PDF is when we put everything together. And we'll do some calculations today to understand these formulas a little bit better. First, I want to talk about layer number 4. And since this is something I hope this into lecture number 1, I'm going to just do it by showing you the notes rather than writing them, which will make it go a little. Please just ask a question and slow me down. So rapidity regulators, what is this tau that we've been avoiding defining carefully? Well, let's first talk about why we need a tau. So it turns out that when you derive the factorization, you encounter situations where you're forced to expand in the linear limit or the soft limit. That's necessary in order to, so there's an integral here. Somebody's talking. So this integral will be a toy example, kind of like the 2 q squared and m squared, and you expand it in 2 different ways to look at the different regions. This is a simpler example even. We have an integral dk plus over k plus with 2 limits, qt and q. And we wanted to calculate that. Well, k plus has different sizes if it's in a collinear region where it's large of order q, or in a soft region small of order q. Well, if you're going to calculate k plus of order q, you would expand in qt goes to 0. So the lower limit in the collinear approximation gets replaced by 0, and now the integral diverges as k plus goes to 0, light cone singularity or rapidity singularity. In the soft approximation, it's the opposite. Now your k plus is of order qt, and you expand it with big Q going to infinity. So you replace the upper limit by infinity. Again, there's a logarithmic singularity, light cone singularity, rapidity singularity. And these singularities are not going to be regulated by dimensional regularization. It just doesn't regulate the singularities. So you need an additional regulator, and that's what this rapidity regulator is. So my magenta factors here are some regulator that I add to the integral. I call it R. It's going to be a function of the loop momenta k and this tau variable, and it's going to regulate this integral so it gives a finite expression. And I might have a different regulator in the linear part and the soft part. There has to be some correspondence between them for things to match up nicely. And different regulators add different factors, these magenta factors in these integrals in different ways. So there's lots of different choices that one could use that have been shown to be consistent. So that's the idea behind this, in a kind of a nutshell, where we encounter these rapidity singularities. It's unavoidable consequence of factorizing things into the TMDs that we want to study. So let me give you a couple of examples. The first example is perhaps the best well-known example of TMDs, and that's Collins' definition of the TMDs. In this definition, what you do to regulate the singularities is you take all those Wilson lines that we had, and remember that they were traveling back along the light cone. You take those Wilson lines and you tilt them off the light cone in a space-like direction. So here's a light cone. This is the plus, minus, and perp components. So plus, minus, perp. And you tilt that vector that's on the light cone, so the path that's on the light cone, a bit off. And so I've done that by adding this exponential of some rapidity yb. In the limit the yb goes to minus infinity, I go back on the light cone. But let's leave the yb finite for a bit, and that regulates the singularities. In pictures, if I go back to the picture up here, what I'm doing is I'm taking this Wilson line here and I'm tilting it in a space-like direction. Okay, so let me try to get it right. Let me do it with this one up here. I'm tilting it towards the z-axis. That's tilting it into the space-like. So that's the kind of thing that I'm doing to the path, and I won't try to draw it for all sides. And I do the same thing for the soft function. Okay, so that's the idea in the Collins regulator. And now the limit of tau going to 0 is replaced by a limit of this yb going to minus infinity. It turns out that you can write the Collins soft function with some work as a 1 over a square root of some soft function. And you can see the handbook for some details and the references in the handbook for further details about that. So this matrix element, this generic thing that we had up there, now becomes something very specific. This YB regulator goes to minus infinity. My PDF depends on YB. This is the bare one, remember, and this is sort of bare in both the rapidity and the dimensional regularization parameter. And my soft function also depends on this YB. You introduce this yn that I mentioned last time also, such that the zeta variable that shows up in the final TMD PDF is given by the sort of x plus dependence from the numerator and this yn dependence that comes from the denominator. In the YB is a cutoff between the linear and the soft, so it cancels between the numerator and the denominator, any singularities that would show up. So each of these needed it separately. The YB was needed to regulate these things separately. But when I put them together, it cancels out. That's the cancellation of the rapidity cutoff, if you like. Okay, so that's a explicit definition with the rapidity now sort of carefully defined and put into the definition. It's not the only definition, so let me give you one more so we can contrast things. So here's a definition that actually leaves things on the light cone, but leaves the paths on the light cone, but regulates things in a little different way. It's called the Eta Regulator. One of the people that invented it is your lecturer on the SET and evolution parts of the school. So you'll hear from Duff about those things. So in this regulator, what you do is you take the Wilson lines, and in the proton matrix element with our staple, you modify them by adding an extra factor like this, k plus over some dim-reg type scale nu. It's a rapidity scale, so like I talked about last time, and you raise it to the minus eta power. So in your integrals, your integral dk plus over k plus gets a factor that's an absolute value of k plus to this minus eta, and that regulates the singularity. Just like in dim-reg, if you have k to the minus epsilon, it regulates the behavior as k gets large or small. Same thing here. In the soft Wilson lines, things are a little more complicated. And the way that this regulator works is you have a kz over nu, not a k plus or a k minus, but a kz. And that actually does the job. It regulates both pluses and minuses to have a kz. In some sense, this is just an approximation of the kz. So kz is the true thing, and you've expanded it and got the k plus for the collinear matrix element, for the matrix element of the staple-shaped Wilson line. It's dominated by collinear regional momentum space. So in this case, with this kz, you have actually, from attachments to the two light cones, you have integrals like this one, dk plus dk minus over k plus k minus. So you have divergences from both k plus and k minus in principle in this integral, and the kz does the job of regulating it. So that's how that one works. And then you put things together, and so now we have f that's got an eta in it. The eta is now taking the place of the tau as the regulator, and I'm taking the limit as eta goes to 0. This is a bare unsubtracted TMD PDF. I have a soft function, depends on eta. And again, the eta dependence cancels between these two things. So when I take eta to 0 at the product, that's fine. There's a finite limit, and I get something well-defined, and then I can do my UV renormalization. In this case here, in this Eta regulator, it's not 1 over root s, it's root s, and that's because the subtraction in this case vanishes. So it's just 1. There's no quantum corrections to the subtraction. So it works a little differently. Now, a very interesting fact is that although these definitions look very different, the place where they differ is just in how they treat the rapidity cutoff. The z here is the same, and actually the left-hand side is the same. The output is the same, it's just the intermediate steps that are differing in the construction. So the final F TMD that you get out, the renormalized quantity, is the same. The factorization theorem, in terms of that renormalized quantity, looks identical in these two ways of constructions. And there's actually a whole bunch of constructions that are like that, that lead to the same TMD PDF, even though they might do the rapidity regulating business a little differently. So that's discussed in more detail in the handbook in section 2.4.1. And I should also mention that not every definition of a TMD PDF falls into this category of giving the same F. So it is possible to construct some that don't. And we have a section in the handbook about that if you're interested as well. It's section 2.5. Okay, so that gives you explicit now, the last layer of the onion that we wanted to probe, and explicit formulas for what with all the details filled in for these TMD PDFs. Now, I know it's a lot to take in. And so I thought that what a good exercise for us to do would be to go through a one loop illustration of the concepts here. We have these very explicit formulas, but really can we get a grasp of what's going on with all these limits, et cetera, et cetera. So I want to walk you through thinking about these formulas, just calculating them in perturbation theory and trying to understand how things work. So that's where we're going next. But let me pause for a second. And I haven't really done anything to notes, so I won't save them. But if anyone has a question at this point, I'll take a question and then we can keep going.
There's one question.
Hi, sorry, I walked in a couple minutes late, so I'm sorry if you already explained this. When you were talking about unsubtracted terms, are you referring to like dispersion relations for the PDFs or?
Yeah, no.
No.
So let me go back. So yeah, so if we look at this formula at the top, this is kind of the generic formula that's true for all schemes. And what it has in it is sort of three different matrix elements. It's got this F, which has a proton matrix element of this staple-shaped Wilson line object, this thing here, that's this numerator. It's got this S, which is this six-sided Wilson line closed loop vacuum matrix element. That's this thing here. And then there's this subtraction in the denominator. And what I mentioned last time, but it probably went by really quickly, is that there's a double counting between this numerator and this numerator. They double count the infrared parts of the matrix element. So you have to remove the overlap. And that's what this denominator factor does. It removes the overlap between the two. You can think of it as kind of a soft approximation to the numerator here, such that there's no soft parts in this blue part, and the soft parts are correctly captured by the green part. And that's an accurate way of thinking about what the denominator is. But the explicit formula for this S twiddle differs depending on how I do the regulation of the rapidity singularities. And that's why I didn't try to write down a generic formula for it.
Gotcha. All right, thank you.
All right, so let's turn to doing some explicit calculations. And again, I just wrote these calculations out, and I figured that it would be a waste of time for you to stare at my handwriting out, very long expressions for loop integrals. So again, we'll just go through it slowly, and it's a nice exercise. So we're going to do a calculation. We're not going to do a calculation with a proton, because I don't know how to do that calculation. We're going to do a calculation with a quark state. So we take the proton and replace it by a quark state. That's fine. It's just doing a partonic calculation. It's an on-shell momentum, so p squared is 0, and I'm just going to take it to have a plus momentum for the external quark. So p mu is p plus. I'm going to regulate singularities with dimensional regularization. I'm going to use dimensional regularization both for ultraviolet singularities as well as infrared singularities. As generally said, you can do that. You can take epsilon and allow it to regulate both, and so we'll do that. Convenient. We'll also use Feynman gauge. I have to pick some gauge for my gluon propagator, so let's pick Feynman gauge. That's the easiest thing to do. And then finally, I'm going to need a regulator for rapidity, and I'll just use this Eta regulator that I introduced. That's the one we picked in the handbook. So, I'm following the handbook so that you have another reference for what I'm talking about here. So I have to calculate the things that showed up in the formula. And in particular, I have to calculate this F twiddle and the S. And I don't have to calculate the S subtraction because I told you that's 1. So we won't even think about it here. I won't go through that. So let's start. So here's the F formula. Remember, it's a bare formula. It's got 2 different types of regulators in it. The regulator is not yet explicit, but it will be in a second. And it's this integral with the staple-shaped Wilson line. So let's just think about diagrams. So it's hard to draw a staple and then attach quark lines to it because it gets really messy. So I made an approximation here. My staple is just this double line. So hidden under the hood is that this double line thing is a staple, but that goes to off to infinity. But that's just a abbreviation for the staple. So there's a staple. It goes between 0 and B. And then there's some quark fields. That's these solid lines. Those are the quark fields hanging out. And I'm taking a quark matrix element, so they're hanging out into the final state or the initial state. Okay, then I have to dress things by a gluon. Now the gluon can attach to the quarks. That's a diagram like this. Or the gluon could attach to the Wilson line. That's a diagram like this. So this means anywhere on the staple. Or you could have a self-interaction between the quarks. That's a wave function normalization diagram. Or you could have a self-interaction between 2 parts of the staple. That's a diagram like this. So these are all the diagrams at one loop that you have, up to mirror images, which I haven't drawn all of. So this one has a mirror, and these ones have this one here has a mirror as well. I just didn't draw them. Okay, so let's think about what the value of these diagrams. Well, this one here is actually simple. It's 0. Why is it 0? Well, we're on the light cone. We're in Feynman gauge. If I attach to the 2 edges of my staple, which are these on the light cone edges, then I get n squared. I get the light cone vector that determines that line. I get it squared because I'm in Feynman gauge. So this would be like nb in my notation here, where this is a light-like vector that tells me the direction of this line. If I attach to there and there, I would get n squared, and it's 0. So those diagrams are just 0. I could also attach to this transverse edge, but that's very far away. And in covariant gauges like Feynman gauge, those diagrams vanish too. So this is just 0, and that's convenient. This graph here in pure dimensional regularization is 0 too. It's a little subtle, but it's 0. The reason it's 0 is that there's a 1 over epsilon UV and a minus a 1 over epsilon IR. It's a scaleless integral, and you just get 0. You have to be careful because you treat UV divergences and infrared divergences differently when you're physically interpreting results, and then you should be careful about setting this to 0 if you want to get the interpretation right. But we'll just set it to 0. That is the answer up to interpreting UV and IR singularities. So it's really these first 2 diagrams that we have to compute. So we just set up things. We give it a momentum P coming in, let the gluon have momentum K, and then we start computing. We need the Feynman rule for the staple Wilson line. So I've written that out here. And B dot K is the light cone direction. And there's no contribution from the infinite staple in Feynman gauge. So I just wrote out pieces from attaching to the 2 sides of the staple that are on the light cone. And that's these 2 pieces. G is the coupling. And then I just start going through it. Well, in this graph, we didn't have a staple contribution. So it's just 2 fermion propagators here, 1 gluon propagator. That's what I've shown in the denominator here. And then some phase factor. The integral over B minus here is the part of the definition. That's this part up here. And then in diagram B, I do have this thing coming in. And so there's for example, this K plus plus I0 is this NB dot K. It's just a plus momentum iconal type propagator that comes in the denominator, and there's only a single fermion propagator, that's the p slash minus k slash over p minus k squared term, and then there's the gluon k squared again. Okay, so these are the loop integrals that you have to do. Now, I denoted that there'll be need for a rapidity regulator. That's this magenta factor here. There's a scaleless term in this integral too, that comes from this one. So I didn't include that. I just wrote plus scaleless. So these are the things that one has to compute to do diagrams A and B. And then it's just a loop calculation. It's one loop calculation like you do in Peskin. Okay, up to the fact that there's this extra integral over B minus. Well, the integral over B minus actually is a friend. It's helping us do the loop integral. So how does that work? Well, if I take this part of the loop integral, that's the only thing that depends on B, and it's just a phase. So just giving a delta function. So I just do the B minus integral, and that gives this delta function here. And then I'm left with whatever parts of the phase are left over. And that's just a transverse phase now. So that's pretty simple. What does this delta function say? Well, it sets the gluon momenta, the k plus of the gluon, equal to 1 minus x times the initial p plus of the quark. So if we go back to the picture up here, p plus of the quark came in, and now this gluon is actually having its plus momenta set to 1 minus x times p plus, i.e. a momentum fraction 1 minus x times the initial p plus. That means that this one here will be set to x times p plus. It carries away the rest of the momenta so that momenta is conserved at that vertex. And that actually makes good intuitive sense, because remember what x was supposed to be. X was supposed to be, when the quark entered the hard interaction, what momentum was it going to carry? It was going to carry x times p plus, and yes, it does. So the formalism is set up to do what it's supposed to do, and it's doing its job. Our calculations are being done correctly. The nice thing from the point of view of the loop integral, this is a ddk, it has a dk plus, a dk minus, and some transverse in d minus 2 dimensions. Well, the k plus is trivial. I just use the delta function. Boom, done. The k minus I can do by contours. I can just look at the denominators and find out where the poles are. I can do that by contours. Then I'm left with the transverse integral to do. And that one I just use standard dimensional regularization type techniques to do. So I haven't gone through the steps. There's more steps in the handbook. So we take the bare coupling, we replace it by our normalized coupling. We're going to work in MS bar types setup. So we have the bare coupling is the renormalized coupling, which is dimensionless, a factor of mu to the epsilon, and then some MS bar type factor that I have to put in. And then I just set things up and do these integrals and combine things together. And I'm showing you the answer here. It's alpha s. Alpha s is g squared over 4 pi. That's g of renormalized g. Some color factor CF, that's 4/3 QCD. Some function of x, a 1 over epsilon pole and a gamma function, and then some transverse bt squared mu squared to the power epsilon. And the rapidity regulator. Actually, the rapidity regulator in this case was a function of k plus. And so it just got fixed to some value by this delta function, and it went along for the ride. It didn't change any of the other integrals. That's also useful. Now, where's the singularity? Well, the singularity is at x equals 1. If I were to take this expression and take x goes to 1, it would blow up. But that shouldn't be happening. And so we have to, what the rapidity regulator is actually doing in this case is regulating x goes to 1. Remember, at tree level, I'd have like a delta function in 1 minus x. So the x goes to 1 is certainly something that I have to consider. It happens in loop diagrams, and it's part of the answer can have x equals 1. But this has a problem at x equals 1 that we have to take care of. And the Eta regulator does that. So the Eta regulator for the linear graph, this magenta thing, is a k plus over nu. This k plus gets to set to 1 minus x p plus. So I get a factor of 1 minus x to the minus eta. That's providing a regulator as x goes to 1. I've written it out here with the generic tau because this is math. So the stuff that's in yellow here is just some math. So let me review some math for you that's useful, not just in this context, but in all sorts of contexts in collider physics. So oftentimes you encounter these types of singularities. There's a singularity if something goes to 1 or 0. And it's always the same way. It could be epsilon, it could be eta like we have here, that something's regulating that singularity. So the generic thing is you get it regulated by this. You had your 1 minus x, and now you get an extra factor of 1 minus x to some power, that I call tau. And this formula Zhenwei already talked about a little bit, but I'll talk about it a little bit more. You have an expansion in terms of distributions of this formula. So this formula, if I expand as tau goes to 0, it is this. So it's given by a delta function term, and then these things that are called plus functions. And there's higher order terms as well that would have log plus functions. What is the plus function? Well, the plus function is a distribution. What does that mean? It means it's a function that's defined when it acts on other functions. Okay, that's the mathematician's definition, but that's good enough for us. So how does it work? This distribution, if the variable is away from that problematic point, it's just equal to a function, simple. But when it at that problematic point, it does something special. And what it does is if it acts on a test function g, any test function g, it subtracts the test function at 1 in the integral, and then does a normal integral with just the normal function f. So if f is singular at x equals 1, then this subtraction fixes the problem because you have g of x minus g of 1, so then you cancel the singularity, and that's how the plus function works. You can also see that if I stuck in g equals 0, that this plus function would integrate to 0, right? If I stick in g, sorry, if I stick in g equals 1, not 0, 1, then I would just be integrating the plus function plane. But if I stick in g is equal to 1, the identity function, this would be 1 minus 1, which is 0. So it would be 0. So the plus function integrates to 0. That's how you can fix this first term, because if you integrate the left-hand side from 0 to 1, all the plus function terms that are higher order terms in this expansion are 0. And you just get the first term, which is a delta function. And that's how you can fix this minus 1 over tau. Okay, so that's some useful math because it allows us to take this formula up here. We put in that regulator factor with this 1 minus x to the minus eta. Now we can just do a series expansion like we want. We want to expand not a tau, but eta goes to 0 in our case, and then epsilon goes to 0. So I'll come back and I'll show you the results for that in a minute. But let's first talk about the soft function. So the soft function is a matrix element of some Wilson loop 2. And we have to do some diagrams for it. There's a virtual diagram like this. There's a real kind of diagram that's kind of a parlance, but like they're really just connecting different sides of this 6-sided figure. If you insert some complete set of states in the middle, then that you can make that parlance of real and virtual more explicit, but let's not do that. So we're connecting sides of this 6-sided Wilson line. We can either connect different sides or we can connect sides that are sort of more like a vertex. These ones are scaleless again, so you get 0. These ones are not, and you get integrals like this. You can go through these integrals again, and you end up with, again, something where this regulator is needed. In this case, there's both the k plus and the k minus singularities, and so you actually need the regulator, the kz that we talked about. Kz is just k plus minus k minus, so you can write it like that. When you do the integral, you end up setting k plus to be k perp squared over k minus. So the k plus that's here becomes a k perp squared over 2k minus. And then you have a k minus integral that's left that goes from 0 to infinity. So it has singularities both at infinity and 0. But this thing with the k minus in the numerator and the denominator does the job and regulates both 0 and infinity. And so it's all good. And you could just do this integral, even though it doesn't look so friendly, but it's not so bad. So that's the soft function. It gets regulated by this too. So now let's look at the results. We go through the analysis, we do the integrals, and we expand. More steps are given in the handbook. So here's what the first part looks like, the F twiddle U. So we get an expansion that has a 1 over tau singularity and it has 1 over epsilon singularities. There's different types of 1 over epsilon singularities. There's a 1 over epsilon IR singularity. It's multiplying what's called the splitting function, PQQ of x. That's this factor up here, this 1 plus x squared over 1 minus x. That's the quark splitting function. If you have seen it before, then you may have recognized it already. And it shows up as a plus function in the answer. And that's actually good because it was supposed to be there. There's a delta function, and then there's this 1 over tau. And there's some logs of bt squared mu squared. there's also a log of zeta. Zeta here is 2 times x p plus all squared in the kinematic setup that I'm using. Okay, so that's what it looks like. And then I calculate the S twiddle. It's also got the 1 over tau singularity. It's got some different logs involving mu squared and nu squared, the cutoffs, and it's got different 1 over epsilon poles. But look what happens when I take this thing and I multiply by the square root of this thing. Square root of this thing basically means dividing it by 2 because it's like 1 plus, and so it divides the perturbative part by half. That cancels this 2 out here, and then these green things cancel. The singularities cancel as promised. And then I'm left with just 1 over epsilon poles after the green parts are gone. See, the whole prefactor here is the same in the 2 parts. And so the green part cancels out as it should, as it was promised to do. And then I'm left with 1 over epsilon UV poles. The 1 over epsilon UV poles are taken care of by that Z factor that does the renormalization. So I just look at the coefficients of them. If I'm using MS bar, which I am, then I just subtract only the poles, and that gives me the formula that I have for this thing. It's got a log of this mu squared over zeta because these logs here and these logs here, when they combine, the nu squareds cancel, and I'm left with mu squared over zeta. And this is, then when I put everything together, all the 1 over epsilons and all the 1 over taus are gone. I take the limits of those things going to 0. I'm just left with something finite. Now that's, when I take epsilon to 0, I'm only removing the UV epsilon. So there's still a 1 over epsilon IR left over. And that's actually important because this thing is an infrared quantity and it has infrared singularities, and it indeed has to have the same infrared singularity that showed up in the longitudinal splitting function, which is a 1 over epsilon IR times this PQQ as a plus function, and indeed it does. So actually, the fact that that's there is important. So that sort of comes out nicely and correctly, and we have a finite expression up to the presence of that 1 over epsilon IR pole. So the 1 over epsilon IR pole is the collinear singularity, and it's indicating that this thing is some infrared quantity. All right, so that's it. That's the calculation. You can go further with this and derive renormalization group equations, and I'm going to leave that for Duff to do. But let me pause here again and take questions.
I may have a question. Oh, sorry, let me ask the question first. Iain, is it, to recap your calculation you just did, is it obvious from this calculation why it's advantageous to compute the collinear function and the soft function separately instead of trying to compute this final TMD PDF directly?
Yeah, because we don't have a formula for it directly. So if we go back, right? So we have this formula, and each of these things is a matrix element, but they're defined as separate matrix elements. And that's, we don't have like one matrix element that includes the 2 things together. We're forced not to do that. And you know, think about where it came from. This thing only knew about one light cone. It was defined with a staple that was sort of along one light cone. It didn't even know about the other light cone. The other light cone was for the other proton, right? So the fact that it came out to be a matrix element only involving this is sort of coming out of somehow the factorization of the one proton from the other proton. The other proton would know about the other light cone. Okay, so that looks good. But there's also this soft radiation. The soft radiation knows about both light cones. So that looks kind of like, oh, you know, but it's sort of simple. It's just this 6-sided Wilson line that's telling us how the 2 sides talk to each other. And the trick sort of to define TMD PDFs is that I take half that soft function and put it in on one side and half and put it in the other side. And then I have matrix element definitions of everything I want to calculate. I see some more questions, so let more people ask questions.
We invite Reed to ask the question on Zoom.
Hi, thanks. When you were canceling the 1 over tau poles between the 2 terms, I don't see what happened to the delta function of 1 over x. Can you see, or 1 minus x,
question.
sorry.
Yeah. So that's because I didn't write every single thing that you need. So let me explain what I didn't write. So I only wrote the 1 loop f. I didn't write the tree level f. And the tree level f would have a delta of 1 minus x. And so it'd be the tree level f delta 1 minus x times the 1 loop s. And adding in an extra delta 1 minus x here. The tree level S is 1, so it doesn't add anything extra here. And that's where the extra delta 1 minus x comes from. It's from the tree level version of this that I didn't write down. Good question.
Thank you.
Okay, one more question in Zoom from Jitayu.
Yeah, thanks. You mentioned that the infinite part of the Wilson line does not contribute in Feynman gauge or light cone gauge. Can you explain why?
Yeah, the part of transverse infinity. Yeah, when you derive the Feynman rule for it, there's like a phase factor that oscillates very, very rapidly and goes to 0 in those gauges. Whereas in a light cone gauge, if you used a light cone gauge, there'd be a finite limit for the Feynman rule. So there's another way of saying it that people often say is like, if you're using a covariant gauge, then those are kind of more localized gauges such that they satisfy the property that as a sort of classical field, the gauge potential goes to 0 at infinity. That's kind of a boundary condition that those gauges have. So that's another kind of way of intuiting it. Or you can just like set up the Feynman rules and take the limit as the side goes to infinity and find what I said.
Okay,
So it would be important in a light cone gauge, but not in a covariant gauge, to take into account the Feynman rule on the side here that's transverse. All right, very good.
Go on.
Thanks for asking all your questions. So now we're going to turn to a part of the today's lecture where actually now I start drawing things again. So I will slow myself down by pause it by writing on my iPad for you. So I want to turn to the process of semi-inclusive deep inelastic scattering. We talked a lot last time about Drell-Yan. Let's add another process to the game that's very important for TMD physics. So this is electron-proton scatter. And from it is produced an electron, explicitly a hadron, that's the semi part of the semi-inclusive DIS, and an X. So it's DIS, but with an identified hadron in the final state. All right, so let's think about this in terms of a picture. So let's say we have our proton coming in. There's our proton. Out of the proton, there's a parton, some momentum K, and it goes into some hard interaction with the lepton. So here's the virtual photon. Here's the electron scattering. Initial electron, final electron. It scatters the quark, and then that quark is going to fragment into this hadron with momentum pH. Okay, there might be some other stuff that happens here. So there could be, again, gluon radiation, et cetera. And there's obviously some other parts of the proton that aren't the one that got scattered by the photon. So this is all this other stuff is just the X, right? So this is how we think about the process. We think about proton electron scattering, in, out goes electron, out goes hadron, and out goes anything else, which is the X. Experimentally, it's a bunch of hadrons. All right, so that's semi-inclusive DIS. And kinematics of it are, well, there's Q squared again, Q being the momentum of the virtual photon. So that's this here, Q. Q squared in this case is space-like. So this is minus Q squared less than 0. So capital Q squared is positive. And then there's a dimensionless variables that people like to define. There's Bjorken's variable X, which shows up even if it's not semi, but it's just inclusive DIS. There's also Y, which is defined as P dot Q divided by P dot L, the momentum of the initial electron. So this guy has momentum L. Write that in. And then there's one more variable that shows up because Y also shows up in classic DIS. And there's one more variable that because the hadron is there shows up, and that's taking P of the initial proton, dotting it into P of the hadron, and dividing by P dot Q, what's called ZH. All right, so that's the setup. Now, we're going to be talking about TMDs, and that means we have to think about what transverse is. In Drell-Yan, it was very easy to think about what transverse is. We didn't even like pause to think about it for 1 second because it was completely obvious what we should do. We just think about like proton-proton collision, along defining the z-axis, and then the transverse axes are x and y. That's what we did in Dralian. Here, it's a little more confusing. So what should define the, there's lots of different frames that we could pick. We have to scratch our heads for a minute and think about what frame to pick. And it turns out that people pick different frames and you have to convert back and forth. There's reasons for picking different frames. So that's part of what makes this process a little more complicated than Dralian. Let me describe things in what's called the photon hadron frame. So in this frame, it's drawn on the right here. You define the transverse axis by thinking about the photon as having no transverse momentum and the proton as having no transverse momentum. That's the same as like in the two protons in Dralian, neither one of them had transverse momentum. Here we're doing it, but not with, we're doing it with the initial proton and the virtual photon. It's a choice. So not a U choice, but it's a choice. So if I do things in that frame, then I find that the final, because I've used up my freedom of defining the transverse direction, now I find that the final state hadron has a transverse momentum. Okay, so I can measure it. And if I think about what it is equal to, it's sort of going to be equal to a piece that comes from the initial quark that goes into the diagram. And then this sort of the hadronization process can change the transverse momentum. So there can be some transverse momentum balance from some going out here. So it doesn't, whatever comes in doesn't have to be exactly equal to what goes out. And that's this PT. So there's a some coming in here and some going out there. And then the final thing is the PHT, the transverse momentum of the pH. And this figure, if you try to decipher it, is saying the same thing as this formula in the end of the day. But I sort of just, it's from the handbook. So I leave it there to see if, and if anybody can understand it. We tried to color it nicely, but it's a little bit confusing, and I don't want to spend a lot of time on it. This is the photon hadron frame. If I look at the cross section in this frame, it's going to look like the following. There's going to be transverse momentum integrals. Let me write two of them, and then let me write a delta function that takes into account this balance of the PHT being given by the ZH-KT. The KT is actually the momentum that comes from the initial proton, transverse momentum. And then this PT that came from the fragmentation process. There's a fragmentation function, D. This is sort of the new thing that depends on that PT, tells us how the transverse momentum has changed in the fragmentation process. And then there's our friend, the parton distribution function, the TMD parton distribution function, which tells us about the KT. So PDF tells us about KT, fragmentation here tells us about the PT. And then the balancing of those gives the total hadron PHT. So that's roughly proportionally what the factorization theorem is going to look like in this case. It's going to have a new object, a fragmentation function. Instead of two PDFs, it's now got one PDF and a fragmentation function. And just like we talked about for Dralian, the like light cone variables just get set to the external ones. So the ZH shows up in the fragmentation function here, X shows up in the PDF here. There's no convolution or integrals in those variables, the only integrals in the transverse variables. So this DIH, which is the new thing, or DHI, not DIH, because the H is taken from the I, right? We have a quark that comes in I, and out goes a hadron H. That's the opposite of the PDF. This DIH is describing the fragmentation of the quark. We can write a similar sentence to what we would write for PDFs, but sort of things are going a little bit the opposite way. So we have fragmentation of an initial quark of flavor I to a hadron H. And the hadron takes a momentum fraction of the quark, right? It doesn't have to take the full momentum of the quark. It only takes part of it. That's actually what ZH is. It's how much does the hadron take of the quark's momentum. And that's why there's a ZH in the D. And there's also a transverse momentum, and that's the PT. And the PT is in the fragmentation function is measured relative to the quark's PT. And that's why the total hadron is given by the quark plus the PT, because the PT is the relative, the difference of this and this. All right, so that's kind of what the new thing that's going to show up. Now we're going to skip all the steps of like going through peeling the onion because we peeled it once. Now we can just jump to sort of what actual formulas are. So there's a formula for, let me write like now a true formula for the cross section. Above one was, a little schematic, there was a tilde in it. Let me write down something that doesn't have a tilde. So d sigma cross section for semi-inclusive DIS, dx, dy, dzh, measuring transverse momentum as well, pht. Well, I'm measuring actually, I'll only measure the magnitude. That'll make my life a little easier. We'll talk about measuring more later. There's some prefactor, which you can look up in the handbook. It's a function of x, y, and q. There's a hard function, just like we had in Drell-Yan, HII this time, not HII bar. They're actually related by q squared goes to minus q squared. And then I'm integrating over angles phi, so I'd put that in e phi a. This is like that's what the vector part of this, the rotation angle in the transverse plane. And then it's easier to write it in impact parameter space, just like it was in Drell-Yan. So let me do that. The phase for the Fourier transform here involves PTH over ZH, just because of the definitions of things. And you'll have to read the handbook to fully appreciate that, because it can be kind of subtle. But you'll have to trust me right now and look at the handbook for further details. And then we have our PDF, Fi of P, with its variables, x, bt, and now putting in the scales. There's a mu scale and a zeta scale. And then we have our D, our renormalized fragmentation function. And it has ZH, BT, and it also has a mu, and it also has a zeta. So I'll call it zeta H. So this is the TMD fragmentation function with all its variables written out. Okay, so let me write one more formula, and then I'll save the notes. So the one more formula I want to write is, what is the definition of this D? So just like we had a definition of the F, the definition of the D is very similar. So Z, BT, we can write it as a field theory definition. And it's got the same type of thing. It's got a limit as epsilon goes to 0. It's got some UV renormalization. The time type we were just doing depends on zeta. It's got a limit for some rapidity regulator that's needed in the construction. And it's got unsubtracted D sub u, z, bt, this is bare, so epsilon, tau, and some, this time it's pH plus divided by z. And then there's some s for the double counting, just like before. And then there's some soft function that I didn't fit on the line. I'll put it down here. Square root. So it's very similar formula, essentially the same. Now the part that differs, so let me get to the part that differs before I pause. The part that differs is, what is this definition of this thing in the numerator? That's quite different because we had this fragmentation process, not the process with the initial proton. So let me write this guy out. So the thing is that it's easy to write out if we keep the intermediate states. So that's what I'm going to do. I'm not going to, in the case of the PDF, I got rid of the intermediate states. The X went away. Here I'm going to leave the X in the formula. So I'm going to sum over all final states X. And I'm going to have it, the initial state is the vacuum. I have a quark field that's producing the quark that's fragmenting. That's this psi. And it's at position B. There's some regulators needed, which I'll throw in. The final state is a hadron as well as anything X. And then it's squared, so I have X in the hadron again. Now on the other side. Probably going to need more room. Squeeze it over. And then I have the kind of opposite situation with a psi bar, I. Alpha and alpha prime are some spinor indices. These W's are some Wilson lines. This one, these fields start at 0. There's also some regulator needed. Tau again, vacuum. Okay, so you think the way you're thinking about it is this is producing a quark, and the quark is fragmenting to the hadron. And then this is the complex conjugate. That's how you can think about the formula. So this is the analog of sort of twisting the PDF, moving the hadron to the outside, and then I can't sum freely over the X states like I would otherwise in the PDF calculation. Okay, so let me pause and see if there's any questions about that before I keep going and describing a little more. I haven't described everything in the formula yet, but I'll take a drink of water. You can ask a question.
Mic's open in the room. Anyone on Zoom?
I think the obvious questions are probably what I'm going to cover next. So maybe we'll just keep going.
Please do.
So B in this formula is like what it was before. It's got a B minus and a B transverse. The thing that's kind of different is this Wilson line. You see that the Wilson line, well, it's not just a staple anymore because I needed to have half of it over here and half of it over there. And that's exactly what I did. I took the staple and I smartly divided it in half. That's what the factorization actually forces you to do. So here, let me draw a picture for it. You sort of have a piece like this extending off to light cone infinity, and then it extends off to transverse infinity too. So sort of infinity in two directions. And then you have the other part. Like this, going to the cube. So think about this as at 0. And this is at the B. And so I go off along the light cone here, off to infinity, like I would do in the staple. And then I go in the transverse direction to infinity. So I've broken my transverse link into a piece that goes to infinity that's yellow and a piece that goes to infinity, comes back from infinity that's red. If I were literally to multiply these two together, I would get back the staple. But I needed to divide the staple in half in some way to put half of it over here and half of it over there. And that's what I've done here in this formula. So let's put the yellow half here. And let's put the red half over here. Okay, so that's a little detail. The Wilson lines here, one thing that's an important detail is that the Wilson lines here went to plus infinity. So in the Drell-Yan case that we were describing, it was like initial state interactions, and the initial state comes in from minus infinity, so the Wilson lines went out to came from minus infinity. Here it's like final state interactions. The Wilson lines are going out to plus infinity. It turns out that when we're careful, that in the part-time distribution functions, the things that we think we understand, the F, I twiddle, in this process, i.e. in semi-inclusive DIS, its Wilson lines are also outgoing. That has to do with the structure of where the quarks were in the hard interaction, that one was coming in, one was going out. You can think about it that way. Or there's more complicated mathematical constructions of exactly how to think about it, or technical constructions, but just a simple picture. So you have Wilson lines that go out to plus infinity, and that is captured by thinking about a Wilson line that you would, in the handbook, we draw it like this for the outgoing to plus infinity, rather than what we were talking about before, which we drew with the curve the other way. Okay, so those two things are slightly different because of the plus infinity choice versus minus infinity. So we could flip our staple around so that it's pointing out to plus infinity along the light cone instead of coming into minus infinity. And we'll see actually that it matters, but for one particular thing, but I'll come to that in a second. Okay, so that gives you, another process where you can measure TMDs. And now we also have this fragmentation function, so we can learn about hadronization. The fragmentation function tells us how a quark turns into a hadron. So we're learning something not only about the confinement of the initial state proton, but also about hadronization, where a quark hadronizes into something like a pion or proton or some other hadron. The next thing I want to talk about comes to kind of classifying all the different types of TMDs that can show up. So far, we've really just talked about processes as if they were unpolarized. We didn't use the fact that we could polarize the proton or polarize the scattering in order to get more information. And you'd heard about that actually in Jinwei's lectures. He talked all about spin. So let's add spin to our story here about TMDs. So consider polarized protons and quarks. That's what we want to do. Polarized protons and polarized quarks. So we'll polarize both the ability, the probe, as well as the thing that is the hadron. It turns out now we have 8 TMDs. You saw them in the other talks in a table that I will also show here. We have 8 TMD PDFs. There's actually 8 fragmentation functions too, but I'll talk only about the PDFs here at leading order. So leading order, remember, means that we're doing this expansion for small qt, so we're expanding in qt over q, and there's 8 of them in that limit. How do we get 8? I want to spend some time describing that to you so you can count to 8 too. So let's consider a more general matrix element than we have so far. I'll call it phi, and I'll give it some indices alpha and alpha prime. It's going to be the kind of same formula that we had before, but I'm going to have these free spinor indices, alpha and alpha prime. Rather than contracting things up with a Dirac matrix, I'll just leave those indices free. Okay, so let's just rewrite the formula that we've had before, but with free indices on the, and I also allow the proton state to have spin. So here's S for the proton state. Psi bar has this index alpha, that's a spinor index. We have our Wilson line. We have psi with alpha prime. I is a flavor index, some regulator, and then same state. Kind of fits. So this is a more general thing because I can vary the alpha and the alpha prime, and I also have this S vector. So the spin is coming into this formula through the alpha and the alpha prime. There they are, as well as through the S. Okay, so that's controlling these two things, the proton spin as well as the parton. The parton's the alpha and alpha prime, and the proton is the S. I want to stop for a second and talk about what S is, because usually when you're talking about a spin a half object, you don't think about like describing it by a vector, S mu, but that's what we're doing. So spin vector, S mu, what is that? So S mu can be written as follows. It can be decomposed into, this is a massive spin a half particle, so it has a longitudinal as well as transverse. And we can break it up as a 4 vector as follows, into sort of longitudinal and transverse parts. S dot P is equal to 0, but we have a piece that's sort of in the Z direction, or more generally in a direction set by this vector here, where this NA and NB are just light cone vectors. So they're 1, 0, 0, plus minus 1 divided by root 2. SL, you can think of as being +1 for spin a half and -1 for spin minus a half in the longitudinal direction. And then but you could also have spin instead you could have spin in the transverse direction, then STX might be ±1, or STY might be ±1, and those are different possibilities for the spin. So this is kind of a useful way of parameterizing the spin of a spin a half object. It's a little bit counterintuitive, but it turns out to be quite useful. ST squared, if I square it, that's equal to -1. So minus ST squared, if I square it, is equal to +1. And it's equal to +1 actually anytime you have a pure state. If it's purely spin up or spin down along one of the directions X, Y, Z, for example, then it's a pure state. But you could also have mixed states, and Jinwei talked about that in his talk. Experimentally, the proton is a hadron and is evolving. And in that case, this S squared would be less than 1 for a mixed state. There's actually a density matrix. When you talk about mixed states in quantum mechanics, use a density matrix formalism, and there's a connection of this object to the density matrix, which we mention in the handbook, and we give you some further references to. So it's kind of nice because we can handle mixed states in this setup. So we need to convert from spinors to this S. That's sort of the NIST. I argue that this S is useful, but how do we get there? Well, if we start with spinors, U bar gamma mu U, well, that doesn't involve S. That's just 2p mu. If I take U bar gamma mu gamma 5, though, then that is actually how I can define S. It's this vector combination. So this is the spin vector, S up to a factor of the mass of the proton. And you can invert those formulas. You can write it the other way around as sort of an outer product instead of an inner product. So it's a matrix, if I write it this way. And then this gives the formula that's in the handbook, which is this formula, where the spin vector is showing up on the right-hand side as an S slash. So this if formula is converting from spinors for the proton. You see in this matrix element, there'd be 2 spinors, one for this proton, one for that proton. You'd have a U and a U bar. Rather than using spinors, we can use this S, and this formula does it for you. There's 2 parts to the formula. You see there's a part with a 1 and a part with an S. And so when we think about the general decomposition of the phi, alpha, alpha prime, there's going to be an unpolarized part with the 1 or a polarized part with the S. And there's only going to be either no S's or 1 S. So that's a constraint. If I think about what is this phi, what could it possibly be? Well, I claim it can be described by 8 hadronic functions. And how do I want to derive that for you? Well, I need to figure out what it could possibly depend on. And one thing it could possibly depend on is the S vector, but it can only have 0 S's or 1 S, and that's a constraint. So let me talk about more generally the constraints on phi and constructing the most general phi. So here's how the constraints go. So I already mentioned no S or 1 S. That's a constraint. So let me say that a little bit better. Linear in S. Those are the 2 possibilities. If I write down some term, it's either got no S or 1 or it's linear in S. What other constraints do we have? We have hermiticity. We could just take the conjugate of the formula for phi, and that's phi dagger. And then we can stare at it for a while and we realize that it's equal to the same thing in momentum space, after we make some changes of variable and do some manipulations, we can show that phi dagger is equal to gamma 0 phi gamma 0, where I sort of hit the 2 Dirac indices with a gamma 0. So that provides a constraint on what I could possibly write down. There's also parity. If I act with parity on everything, then it turns out that that's also gamma 0 phi gamma 0, and that provides a constraint because QCD satisfies parity conservation. There's no constraint from time reversal, and I'll come back to that in a little bit. But there's one more important constraint that's a little more subtle, and that is what's called good quark fields. You see, so far, none of the constraints had anything to do with about our QT squared over Q squared expansion. And this good quark fields is where that comes in. When we want to get the leading order terms, we have to make use of what are called good quark field terms. And those terms satisfy the following projection relation. Gamma minus gamma plus divided by 2 on the field psi equals psi back. That's a projection relation. And hopefully Duff will be able to explain to you where that comes from in SCT in his lectures, and why that gives the leading power terms. So if I impose those 4 constraints, I can write down the most general phi. And so let me do that for you. So phi has the following terms. F1 gamma minus. Basically, this projection relation on the good fields means there has to be a gamma minus. Remember that there's two sides, the two indices, alpha and alpha prime. I can hit either one of them with a projector. And that forces me to write down things that involve a gamma minus. Otherwise, I would get vanishing terms. So basically now when I write down the most general thing, it's got 8 terms. And that's where the 8 terms come from, the terms that satisfy this constraint. So I have terms that have spin, 4 terms that don't. The first term didn't, the second term does. I have terms that could have the longitudinal spin. If I write down an ST, I have to dot it into something. So in the first time I dotted it with an epsilon, this time I dotted it just into the K. This is giving what's called the G1T perp term. And my handwriting has got me into a little bit of trouble to squeeze it all in. Nice thing about the iPad is you can always save yourself a little bit of space if you need to. Move things over, then you can squeeze in your gamma 5 and your gamma minus that need to be there. A term like this with the ST slash. Here's a term like this. Again, kt.st over m. H1t perp. This has a kt slash, a gamma minus, and a gamma 5. Balancing dimensions with an m. Then there's one final term, h1 perp. Sorry, h1 without the perp up here, h1 without the t, kt slash gamma minus, no spin in this one, m. Okay, so this formula has 1, 2, 3, 4, 5, 6, 7, 8 functions. 8 TMDs. So that's where the 8 TMDs that show up at leading power are coming from. And I leave it as a homework exercise for you to check that I wrote down something that satisfies the constraints that I wrote down. So in these tables that you've seen, so here's the table that you've seen before, this is where the 8 functions come from. So we have these 8 functions. Now they're just sort of organized in a nice way. So they're organized by the nucleon polarization, unpolarized, longitudinally polarized, or transversely polarized. That's whether there's no S for the unpolarized, there's an SL for the polarized, for the longitudinally polarized, or there's an ST for the transversely polarized. That's the rows here. And then the quark polarization has to do with the spin of the quark, whether it's unpolarized like the gamma minus is the unpolarized, that's the F1 here, which we've talked about so far. But there's also an F1T perp, and that F1T perp also just has a gamma minus, so it has the same unpolarized quarks. And then there's other possibilities like gamma 5 gamma minus, that's a longitudinally polarized quark, or having a gamma perp, that's a transversely polarized case. And that's the H's. So the G's are the longitudinally, the H's are the transversely, and the unpolarized are the F's. And that explains this table that you've seen several times. The table has names associated with various people and other things associated to the history. And I'm not going to go through it, but we'll talk, about these things, and they're interesting. And they encode the spin orbital correlations of the TMD, as Jinwei has emphasized to you. So they, and you see explicitly in this formula those spin orbit correlations with a kt.st or kt cross st type term showing up here, or the kt slash. All these things are kind of made very explicit. Was there a question?
Yeah.
No, that's hallway
Can I
noise.
Oh, sorry to interrupt. Can I ask a question?
Please do, go ahead.
Yeah.
Yeah, sorry. I was disconnected and reconnected at a point. Can you explain again why the phi has either no S mu or linear in S mu? Why there is no high terms in S mu?
Yeah, you missed something important. I'll explain it again. So when you think about the matrix element that you're talking about here, protons are spin a half. So you expect a spinner for the state for the proton. Well, there's 2 proton states, so you expect a U and a U bar. for the proton. And I traded the U and the U bar for the spin vector S. And I'm not going to go through the full derivation, but here's the formula. So describing the spin in terms of U spinners can be traded for this S vector. And it describes all the different spin polarizations. But this formula either has a 1 or an S. It's linear in S. And so there only can be one S. It's not like a general function of S, because the spin is, it's just spin a half, right? It's not like spin 1,000.
Okay.
We're not combining 1,000 particles of spin a half or something and trying to talk about all the different things that could happen, in which case we'd need a more complicated S, but we could do it the same way actually with a linear S if it was a complicated enough one. But anyway, so it's basically because of the fact that the proton is spin a half, so there's only so many possibilities, and they're all encaptured by having a single S.
I see. Okay. And
This
also
formula
because
is-
in the operators, we only have 2 quark fields.
Yeah.
Right. Yeah. Okay. Gotcha. Thank you.
I mean, the hadronic part would be a single S, even if I had a more complicated quark part. The quark part's the alpha and the alpha prime.
Yeah.
So the
Okay.
fact that it's
That's
linear in S is because of the proton has spin a half, not because the quarks have spin a half.
Sure. Okay.
Yeah.
Gotcha. Okay. Now I understand. Yeah.
Yeah.
Okay.
The matrix
Like
part of this thing is the quark fields. That was important, that it was just psi bar psi with an alpha and alpha prime. If I had a 4 quark operator with an alpha alpha prime, beta beta prime, then I'd have a more complicated tensor, right? But I'd still have a linear in S.
Gotcha. Okay. Thank you.
Okay, so now we're going to come back to time reversal. I didn't use that as a constraint. Why? Well, time reversal is kind of interesting. Under time reversal, S goes to minus S. And actually, naively, 2 of these objects, this one here and this one here, if you go through it, you find out that they're odd. So that's kind of it. If they're odd and QCD respects time reversal, because we think the theta function, the theta term in QCD we know is very, very small, so let's throw it away. So these functions are odd, you might expect that they vanish. The rest of them are even, so fine, but these ones are odd. But there's a key thing that happens also when you do time reversal, and that's that the Wilson line directions switch. From the past pointing, minus infinity, to the future pointing, or vice versa. So our W's that were going to plus infinity get swapped with W's that go to minus infinity. And therefore, we're talking about a different matrix element with a different Wilson line. It's a similar looking Wilson line, but it points in a different direction. And that actually is physically distinct. So I said that one of those Wilson lines came into semi-inclusive DIS, that was the plus infinity. The other came into Drell-Yan, that was the minus infinity. So actually what you learn by using time reversal is these formulas, that the Sivers function for semi-inclusive DIS is the negative of the Sivers function for Drell-Yan, and likewise for the Bohr-Mulders. This is the famous SIDIS sign flip that comes about when you relate the formulas that appear in the 2 cases. Originally, it was due to Brodsky, Hong, and Schmidt, where they did a model calculation and saw this sign flip. So models can be very useful. We've been talking all about QCD here, and like you'll have lectures on lattice QCD, but sometimes you learn things from models, and there's a whole section in the handbook on models, and it also goes through the history of this calculation of Brodsky, Hong, and Schmidt. It was Collins that put this on a rigorous QCD footing, and it talked about the sign flip of the Wilson lines derived these formulas. All the other ones are equal in SIDIS and Drell-Yan, but these ones come with a sign flip. Now, in the handbook, we write this a little differently because we contract up the alpha and alpha prime indices with some gamma structure. So we contract it with a gamma plus gamma 5, or a tensor sigma alpha plus gamma 5. And then we get the F's and G's and the H's, and we write it this way. But this formula here is just another way of writing this formula that I wrote up here. So it's not some different thing, it's just the same thing. Now, when you actually want to do factorization for all these things, you need to sort of think about whether I've so far talked about everything in momentum space, and some of the symmetries I imposed were actually easier to impose in momentum space. But when I want to write the factorization, I need to Fourier transform to position space, right? BT was much simpler for talking about factorization. So now I've got these formulas here that I need to Fourier transform. You say, oh, okay, well, that's not so big a deal. It's just a Fourier transform. It's a little bit tricky. And that's because here you've got a scalar function of KT, and there's no prefactor. So that's easy to Fourier transform. But here you've got a scalar function of KT times a KT row, and you got to be careful about that when you do the Fourier transform. It's not so bad, but you have to be careful. And some of the terms even have 2 KTs. So, you have to be more careful. But you can do it. And so the Fourier transform is another formula in the handbook. Here's the decomposition of the Fourier transform in terms of scalar objects in BT space, and KTs that were out front become now BTs that are out front. And the formula looks pretty similar other than that. But the details are hidden in the Fourier transform. And these objects that are showing up here, these blue objects, are kind of Fourier transforms, but transforming those extra KTs as well. And so the kind of general formula looks like this. There's some KTs to the power n that get Fourier transformed. If I do the phi integral, because everything's a scalar in magnitude KT, there's some Bessel function that shows up. And so these F's in here are actually have some derivatives of the formula, or KT weighted integrals with a Bessel function of the scalar objects. And this is how the blue objects are related to the red objects. So that's a little detail, but if you want to learn more about it, then I invite you to go through an example of that in the handbook. So in the end, it's going to be these blue objects that I'll write down in the factorization for processes that we'll talk about in lecture number 3. When we talk about actually how do we measure these things. So we talked about how to define them, but I wouldn't have gone to all the trouble of defining them for you if we couldn't also measure them. And that's going to be something we'll do in the 3rd lecture. I should also mention that there's a similar spin decomposition that you can do for fragmentation functions. It's in the handbook. For gluon TMD PDFs, it's in the handbook. And gluon fragmentation function in the handbook. Section 2.7, lots of good stuff in there. Have a look. In these lectures, we're not going to need very much of that extra stuff. We're just going to need one little bit of extra stuff. And that's for the fragmentation functions, there's also spin dependent table. I've cut it off. It looks very similar to the PDF table that I showed you, but I just took the part that I needed. And that's because I'll think about only a pion or an unpolarized hadron as my final state fragmentation product. Then I just need this row here, and I have the unpolarized D1 function, and with the quark polarized, I can have another function called the Collins function. So those are the 2 fragmentation functions, and all the formulas for the decompositions and stuff like that. It's all in the handbook for the fragmentation functions too. Okay, so I think this is probably a good place to stop. I have one more slide, but I'm going to leave it for lecture number 3, just so we have some time for questions today, and then I'll come to that in lecture number 3.
Well, first, let's thank Iain for lecture number 2. Questions in the room?
Save the notes.
Questions on Zoom? Andrew has a question.
Yeah, I have a question, but it's not necessarily it's the TMD stuff, but I just never thought of it before. When you're doing these things in D equals 4 minus 2 epsilon dimensions, or actually if you're just in 4 dimensions, it's easy you could say you have your gamma 0, gamma 1, you can enumerate these gamma matrices, and there's a natural way of defining, say, gamma 5.
Yeah.
Does that definition change if you go to 4 minus 2 epsilon, where things are continuous?
Absolutely,
now? What's the next one?
Yeah, so gamma 5 is like there's like a history to gamma 5 in D dimensions, and it is kind of subtle, and there's different schemes for it. And it has to also do with how you think about, like, when you extend the gamma matrices to D dimensions, now you have an infinite number of them. You have like 4 minus epsilon, so you have epsilonic number, but it's continuous, so you have kind of an infinite number. And the subtleties are related to how you think about the gamma matrix commuting or anti-commuting with the gamma 5. And it turns out that there's different ways of doing it. There's sort of naive, there's like what people call naive gamma 5, and that's just like you take what was true in 4 dimensions and you extend it to epsilon and you just proceed. It turns out that that actually fails in some aspects of quantum field theory. In particular, it fails to get the anomaly right. So if you calculate triangle diagrams with that construction axial anomaly, for example, pi 0 to gamma gamma, just get it wrong. So that scheme is doing something weird, and it's actually doing something a little weird with gauge invariance too. And it turns out there's something called the de Hooft-Veltman scheme, which is a smarter scheme. And it uses both commutators and anti-commutators, but commutators, I forget which one goes where, but like one for the epsilonic dimensions and one for the 4-dimensional parts of the gamma function have different, they satisfy a different algebra of the gamma 5. That one works very nicely, gets the anomaly right. So there are definitely subtleties. Collins has a book called Renormalization that has a very nice chapter on this, on these subtleties. So I refer you to that as a source.
Okay, thank you.
Yeah.
I'll ask a question while other people are deciding whether they want to ask a question. So Iain, can you elaborate on your comment that the F tilde, the TMD PDF that appears in SIDIS has a future pointing Wilson line, and you mentioned that's related to how the hard scattering interacts with the quark. Can you elaborate on why that leads to an outgoing Wilson line? And,
Sure. So if we go back to it up here, if you think about this, is this quark was incoming, it's going to be in the PDF. Remember that this picture that I had last time, right, where the Wilson line was generated by the interactions with the other quark in the hard process. And I mentioned like we could replace it by a Wilson line as a sort of proxy for, because it's like very energetic in a different direction. That's what the hard collision did. So you can think about this collinear in one direction. This is like N collinear in this SCT language, this is N bar collinear or something like that. We're replacing this one by a Wilson line, but it's outgoing. And that's why the Wilson line is outgoing. That's like a simple picture. A more complicated picture that gets to the same thing is to think about contour deformation and what you have to do when you derive the factorization theorem. And that'll also get you to the same picture as it having to be plus infinity for the DIS process.
ordinary DIS, like the collinear PDF, there it is. I guess the Wilson line just connects two different quark fields.
That one doesn't matter.
Yeah.
Like you can use either one in that case because you have plus infinity, like you have a Wilson line. If you think about it along the way, it's like Wilson line going off to plus infinity, and then it comes back. But then the part that goes off to infinity cancels, and you end up with a finite segment. And so you construct the finite segment whether you use the plus infinity or minus infinity. So you don't really think about it.
Here it matters because the two segments are separated in the perp direction, so and they don't cancel.
Exactly.
Was there a question? Speak this direction.
Okay. So you mentioned on 13 that naively the like Sivers and four molders are time reversal odd.
Yeah.
And you said something about Wilson lines. How does that play into it? Like,
Yeah.
about
Good.
that?
So let me explain more slowly. So when you go through this decomposition up here, I could have added another bullet that was time reversal. Actually, originally people did. And when you have time reversal, it it provides another symmetry, and I can impose that on the phi and see what it imposed. Because the S goes to minus S under time reversal, the spin vector flips. It turns out that if you look at, for example, just these first terms, it turns out like there's no S here. This one's even under time reversal, so it's all good. The S flips here and everything else is even. So it looks like this term just goes to negative itself. And if you have some function that's equal to its negative, that function is 0, right? So that looks like something that because of time reversal, you'd be actually ruling out the presence of this term, the Sivers term. And people thought that for a while, but then there was this calculation of Brodsky, Huang, and Schmidt that showed like in an explicit model calculation where there was final state interactions that were really driving the physics and giving a non-zero result, that you got a non-zero result. So what was going on? And it was realized that there's important difference between outgoing Wilson lines and incoming Wilson lines because they interact differently. They describe different physics, final state interactions, initial state interactions. And when you do the time reversal, if you go back to these pictures I had at the beginning, see here, the z-axis is here, the t-axis is here. This is going backwards along the light cone. It's back in time. The staple that you have for the SIDIS is the opposite. This thing would extend forward in time. Those two staples are physically distinct, it turns out. You can think about why they're physically distinct. They're physically distinct. One way of thinking about it is that there's other particles in the final state, like the other quarks in the proton that didn't get hit by the quark field. Those other quarks in the proton just go along into the final state. They do something, and they could interact with the Wilson line if the Wilson line's also in the final state. So there's a distinction between having, so those are kind of a final state interaction that can happen in the case when it's outgoing and is different when the case when it's incoming. So having this thing point backwards along the light cone or forwards along the light cone actually gives different answers. And time reversal is switching exactly time, and the switching exactly time in this figure is the difference between pointing forward along the light cone or backwards along the light cone. And so that's what the time reversal does. It flips this from pointing that way to pointing the other direction. And it flips you from the Wilson line that's relevant for Drell-Yan, which is pointing backwards, to the Wilson line that's relevant for semi-inclusive DIS, which is pointing forwards. And that's what this little comment that I had here. So I could little add to it. This is sort of SIDIS, Wilson line, and this is the Drell-Yan Wilson line. And that, therefore, what you get from time reversal is not like zero, but you get a relation between the SIDIS function and the Drell-Yan one, and you find that they're differing by this sign. They're different functions because the Wilson lines are different, but the time reversal still tells you something. It actually tells you that under that flip, there's still a sign, there's an overall sign flip, so they're the negative of each other. It's a prediction of QCD factorization that that's the case. And experimentally, we're trying to pin that down and figure out, can we test this prediction of TMD factorization? It's a very fundamental prediction of the whole formalism. So we'll talk a little bit next time about that.
One more question in the room.
So I was just going to ask, we use time reversal symmetry as well as parity in this early on. I was wondering if you could also use the other like this discrete symmetry of charge conjugation or to further restrict.
Yeah, you can use charge conjugation, and I didn't talk about it, but charge conjugation relates the quark TMD PDF to the anti-quark TMD PDF. So those are two different things. Like when we sum over flavor, we sum over U, D, S, but there's also U bar, D bar, S bar. Those are different TMD PDFs. And what charge conjugation is doing is sort of giving you, it's not going to the same thing, it's going to something that would annihilate, if you're annihilating a quark, you'd go to something that would annihilate an anti-quark. So you're not getting back the same TMD PDF, so you're not getting back the same phi, therefore we're not using it.
I don't see any more questions here. How about on Zoom?
Well, you could use charge conjugation if you wanted to consider antiprotons.
I don't see any more questions, but we have one more lecture at which you can vote in any more questions. So thanks a lot, Iain.
Yep. See you after your lunch.
I'll close the Zoom meeting during lunch and reopen before 2 p.m.